All right. Strap in, everyone, for this deep dive.
Buckle up.
That's right. Buckle up for this deep dive we've got today.
Absolutely.
It's a special one, tailored specifically for you.
Oh.
You, a university student out there navigating this wild world of material science and engineering.
Sounds familiar. Yeah.
Now we're diving into a chapter all about material failure.
Ooh, exciting stuff.
Now I know what you're thinking.
What am I thinking?
Oh, no, another textbook chapter.
Textbook.
To cram for.
Gotta cram.
Right.
Yeah.
But trust us on this one.
Okay.
This isn't about just passing that exam.
No.
We're going way beyond that.
Okay.
Giving you the knowledge, giving you the tools to actually apply this stuff
Right.
to real-world engineering.
Okay, so practical.
So think safety, choosing the right materials, and preventing those big catastrophic failures.
Yeah, the ones you hear about in the news.
The ones that make the headlines.
That's right.
Exactly. So
Yeah.
it's all about...
Take that theoretical knowledge, take it from the textbook, and actually turn it into something usable, right?
Exactly. And let's face it, understanding why things break,
Right.
that's pretty crucial.
Oh, absolutely crucial, especially when you're thinking about building bridges,
Bridges,
designing aircraft.
designing aircraft, I mean,
those are
high stakes.
high stakes.
Yeah.
And this chapter
Yeah.
starts off with something I think we've all experienced at one point or another.
I hope so.
That struggle, that annoying struggle to open
Yeah.
a plastic package.
The worst.
You know what I'm talking about.
Oh, I know
You're
exactly.
digging your nails in there.
You got to get the scissors.
You're trying to find a starting point.
Exactly.
Turns out that little notch you're creating to get in there, it's actually demonstrating a key concept, stress concentration.
Oh, that's interesting.
It might seem small,
Tiny little notch.
but that notch is acting like a magnifier.
A magnifier.
So it's stress.
It's making the material weaker at that point.
Right, right.
And this isn't just about frustrating packaging.
It goes beyond that.
This chapter shows the same principle at work
Okay.
in a photo of a massive oil tanker
Oh, wow.
that literally cracked in half
Oh, no.
because of a crack.
Because of a crack.
Imagine the forces at play there.
Huge forces.
Talk about a real-world example.
Wow.
It's incredible how a tiny flaw
Yeah.
can lead to such a catastrophic failure.
That's a great point. And the chapter also mentions the Aloha Airlines Flight 243,
Yeah.
the Boeing 737 that, basically ripped open mid-flight
Oh, yeah.
due to fatigue and corrosion.
Yeah.
I mean, these are,
Scary things.
it just really drives home the point
It does.
that understanding material failure isn't just some academic exercise.
Yeah.
It has huge real-world consequences.
Absolutely. These failures can have
Right.
enormous
Right.
economic and human costs.
That's right.
Which is why it's so important to understand these different ways materials can fail.
The different ways, yeah.
For instance, the chapter dives into
Yeah.
ductile versus brittle fracture.
Ductile versus brittle, yeah.
Now, a ductile material,
Okay.
it's going to stretch.
Okay.
It's going to deform,
Yeah.
giving you a warning before it breaks.
Yeah.
While a brittle material just snaps.
Snaps. No second chances.
No second chances.
Big difference.
So if you're building a bridge,
Oh, if I'm building a bridge.
you probably prefer it to be made of a material that gives you a little heads up
Some warning signs, please?
before it collapses.
Yeah, precisely. And you can actually see the difference between those types of failures
Okay.
just by looking at the fracture surfaces.
Oh, interesting.
The chapter shows some images
Oh.
of a ductile fracture,
Uh-huh.
and it's got this really distinctive cup and cone shape.
Okay.
And then in contrast to that, you've got the brittle fracture surface, which is flat, almost featureless.
Really?
Yeah, it's like looking at fingerprints of failure.
Wow, that's crazy.
It is, isn't it?
There's even a close-up
Oh.
image
Okay.
of a ductile fracture under a microscope.
Okay.
And you can see all these tiny dimples.
Wow.
It's like looking at a miniature,
Miniature.
landscape formed by the material pulling apart.
That's amazing.
And those microscopic features, they tell a story.
A story, yeah.
They can reveal how that crack initiated and how it propagated.
It's like detective work.
Yeah.
But at the micro level.
So how do engineers actually predict when something's going to break?
That's a great question.
The chapter mentions fracture mechanics.
Fracture mechanics, right?
Honestly, it sounds
It's a little intimidating.
a little intimidating.
The math can get complex.
Yeah.
But the core idea is actually quite simple.
Okay.
It all comes back to
Yeah.
that stress concentration we talked about.
That notch.
That notch, right?
The longer the crack
Okay.
and the sharper its tip,
Uh-huh.
the more likely it is to grow under stress.
That makes sense.
Okay, so that makes sense. But then
Yeah.
how do engineers design
Yeah, how do they actually design it?
structures to resist those cracks?
Right, so that's where fracture toughness comes in.
Fracture toughness.
It's this material property
Okay.
that tells you how much resistance it has
Okay.
to crack propagation.
Okay.
Think of it like the material's ability to tough it out,
To tough it out.
even with a crack present.
I like that.
Yeah.
So a material with high fracture toughness.
Yeah.
Like it's like a superhero.
He's a superhero material.
Able to withstand more punishment before giving in.
Exactly.
I like that analogy.
And the textbook actually has
nice.
a really handy table
Okay.
comparing the fracture toughness of
Right.
all different kinds of materials. So
Right.
you can really see how crucial material selection is when it comes to engineering design.
That makes sense.
Yeah, and it's not just about the material itself,
Right.
The chapter also talks about how engineers can actually design structures to minimize these stress concentrations.
Okay.
But like think about smoothing out sharp corners
Okay.
or using special techniques
Yeah.
to introduce compressive stresses
Okay.
that help prevent cracks from growing.
So it's like giving the material a little extra support.
Exactly, yeah, just making it more resistant to those weak points.
I like it.
But what about situations where a material experiences like a sudden impact?
Okay.
That's where impact testing comes in.
Impact testing.
Yeah, the textbook describes this test called the Charpy test,
Okay.
and they basically use a swinging hammer
Oh, wow.
to fracture a notched specimen.
Sounds intense.
It's pretty dramatic,
Yeah.
but it simulates these real-world scenarios
Okay.
where materials have to withstand those sudden shocks.
Yeah, like car crashes.
Exactly, car crashes, falling objects,
Things like that.
that kind of thing.
And what's interesting is that some materials,
Mm-hmm.
especially certain types of steel,
Right.
they become much more brittle
Yes.
as the temperature drops.
Like temperature drops, yeah.
The chapter even tells a story
Oh,
about these World War II ships
okay.
that fractured in cold water
Really?
because of this phenomenon.
Wow, that's a chilling reminder
It is.
of how important it is to consider these factors
It is.
in engineering design.
Yeah, you definitely don't want your ship
No,
cracking in half because the water's too cold.
not at all. It highlights the importance of understanding,
Yeah.
how temperature can influence a material's behavior
Right.
under stress.
Okay, let's move on
Okay.
to another type of failure.
All right.
It's often called the silent killer,
Uh-oh.
fatigue.
Fatigue the silent killer? That sounds ominous.
That does sound kind of ominous.
What is that?
What exactly is fatigue?
So fatigue is the kind of failure that happens gradually
Right.
over time due to repeated stress cycles.
Okay.
And what's surprising is that it can occur even when the stress is below the material's yield strength.
So below the point where you'd expect it to start permanently deforming.
Exactly.
So it's like bending a paper clip back and forth until it finally snaps.
That's a great analogy.
It might seem fine for
Yeah.
a while, but those repeated stresses
Uh-huh.
eventually take their toll.
They do, and it's actually a staggering statistic.
Oh.
90% of metal failures
Wow.
are attributed to fatigue.
That's a lot.
It is a huge number.
So that's why engineers use something called an SN curve
SN curve.
to predict the fatigue life of a material.
It's basically a graph
Okay.
that shows how many cycles of stress a material can withstand
That's what I'm
before it fails.
So they can use this curve
Yeah.
to estimate how long a component will last
That's the idea.
under certain conditions. Yeah, that's pretty crucial information
Yeah.
for designing things like, airplane wings or bridge supports.
Absolutely. And when you look at a fatigue fracture surface,
Uh,
under a microscope, you can actually see
you can see it.
evidence of those repeated stresses.
It's amazing, isn't it?
There are these telltale marks called beach marks or striations
Beach marks, striations, yeah.
that show the crack slowly growing over time.
It's like the material is trying to tell us its story,
It is.
leaving behind clues about how it failed.
And speaking of stories,
Oh,
did you know that engineers can actually take steps
okay.
to extend the fatigue life
They can.
of materials?
How do they do that?
For example, they can smooth out those sharp corners
Right.
that we talked about earlier, or even introduce compressive stresses on the surface to make it
Okay.
more resistant to those fatigue cracks.
So they're essentially trying to outsmart fatigue
Yeah.
by making the material tougher and more resilient. Exactly. It's like giving the material an extra layer of protection
Yeah.
against those repeated stresses.
But there's another type of failure.
Oh,
we haven't talked about yet.
okay, hit me with it.
Creep.
Creep.
What is that?
What kind of failure is that?
So creep is a slower, more insidious kind of failure
Okay.
that happens over long periods
Okay.
under constant stress, often at high temperatures.
Okay.
So think of it as the long game of material failure.
So it's not a sudden snap,
No,
like a brittle fracture.
not like the...
More of a gradual deformation over time.
Precisely. Yeah, it's what can happen
Okay.
to jet engine turbine blades
Okay.
or power plant components
Right.
that are constantly exposed to high temperatures and stresses.
So even if the stress stays the same,
Yeah.
the material can still continue to deform?
It can't. It's a challenge for engineers.
That sounds like it.
It is. And temperature plays a big role in this.
Okay.
Higher temperatures mean faster creep, shorter lifespan for the component.
That makes sense.
And the chapter actually shows a typical creep curve.
Okay.
It's a graph that illustrates how the strain increases over time,
Okay.
even under a constant load.
So engineers are essentially trying to predict
Yeah.
how long a component will last before it creeps too much.
Right.
Becomes unusable.
Exactly. And for those really long-term applications,
Okay.
like power plants that are designed to operate for decades,
Right.
they use something called the Larson-Miller parameter
Okay.
to predict creep rupture,
Creep rupture.
which is the point where the material finally fails.
So it sounds like predicting and preventing creep
It's a big deal.
is a very complex, crucial aspect
It is.
of designing for high temperature applications.
For sure.
So we've covered fracture,
Yeah.
impact testing, fatigue,
Uh-huh.
and now creep.
Creep.
It's incredible how many
That's fascinating.
materials can fail.
It really is.
It really highlights the complexity
It does.
of material behavior and the challenges that engineers face
They face a lot.
in designing safe and reliable structures.
Absolutely. But you know what's interesting is that
But this chapter also shows that engineers have developed like an arsenal
an arsenal,
of tools and techniques to understand and combat
right?
these failure modes.
Like detectives.
They're like detectives,
Yeah.
analyzing the clues left behind
Yeah.
by these failed components
Right.
and using that knowledge
To build better.
to build better, stronger, more resilient structures.
That's right.
It's amazing to think
Yeah.
that something as seemingly simple as
Right.
choosing the right material
Uh-huh.
or smoothing out a sharp corner
Those little things.
can make such a big difference
They can.
in preventing failure.
It really underscores how important it is to understand these concepts.
It does.
Not just for engineers,
Yeah.
but for anyone.
Anyone who interacts with the physical world.
Right, exactly.
So let's recap
Okay.
what we've learned.
Let's recap.
We started with that relatable experience
Yeah.
of struggling to open a plastic package
The worst.
and discovered the concept of stress concentration.
Right, those little notches.
Then we explored the dramatic differences
Yeah.
between ductile and brittle fracture,
Totally different.
seeing how those tiny cracks can propagate
Uh-huh.
and lead to those catastrophic failures.
Absolutely.
We even delved into the microscopic world,
What he did.
examining those fascinating fracture surfaces
Like a little landscape.
that reveal the story
Yeah.
of how a material failed.
That's right.
And we learned how engineers use impact testing
Uh-huh.
to simulate real-world shocks
Important stuff.
and understand how temperature can affect a material's behavior.
Exactly.
Then we uncovered the silent killer, fatigue,
Fatigue.
and saw how repeated stresses can weaken
Yeah.
even the toughest materials over time.
It's sneaky.
And we explored creep,
Ugh.
that slow and steady deformation.
The long game.
That can happen under constant stress, especially at high temperatures.
Right.
It's been quite a journey
It has.
through the world of material failure.
The world of material failure. Fascinating stuff.
It really has, but instead of feeling overwhelmed
Yeah.
by all these ways things can break,
Right.
I actually feel empowered.
Empowered, yeah.
Knowing about these failure modes
Uh-huh.
and how engineers are working to prevent them,
That's the goal.
it makes me feel more confident about the structures
Yeah.
and materials we rely on every day.
That's the beauty of knowledge, you know.
Yes, it is.
It replaces fear with understanding.
Yeah,
And it gives us the tools to create a safer,
Yes.
more reliable world.
absolutely.
Yeah.
So to wrap things up,
Okay.
I have a challenge for you.
A challenge, right?
As you go about your day, look around.
Okay.
Think about the materials and the objects you use.
All right. I'm listening.
Consider how they might be susceptible
Okay.
to the different types of failure we've discussed.
Okay. I'll keep that in mind.
You might be surprised
Yeah.
by what you discover.
I bet I will.
And remember,
Yeah.
failure is a part of life,
It is.
even in engineering.
That's right.
But by understanding
Yeah.
how and why things break,
Right.
we can learn from those failures
Learn from our mistakes.
and design better, stronger, more resilient solutions for the future.
Absolutely.
So keep exploring, keep learning, and never stop being curious about the world around you.
That's great advice.
Until next time.
See you then.